Hello, this is Yang Tan, and the topic of my talk is the mistakes of a popular protocol calculating private set intersection and union cardinality and its corrections. This is a joint work of me and Bolu. The contributions of this paper. First, it points out mistakes of the most popular PSI-CA protocol. And second, the corrections of this PSI-CA protocol, as well as its extended PSU-CA and the PSI Protocol. Third, we will present you a new security proof of the corrected PSI-CA protocol. And fourth, the implementation of this protocol. The contents of this presentation is listed as follows. First of all, I will describe some basic definitions. Second, the introduction of the original PSI-CA protocol and why it is wrong. And third, I will correct this protocol. Fourth, the security proof of the corrected protocol. And the fifth, the simulation and the implementation of the protocol. The first section is the basic definitions. Some basic definitions involved in this paper. First of all, it's the definition of the private set intersection cardinality protocol. It's short for PSI-CA. This protocol has two parties. Server, it has a private input set with the W items S sub 1 to S sub W. And the client, it has a private input set with V items C sub 1 to C sub V. This protocol outputs the cardinality of the intersection set. The second definition is the private set intersection protocol, also short for aka PSI. It has the same parties and the same inputs. This protocol outputs the intersection set. And the private set union cardinality protocol, aka PSU-CA. This protocol has the same parties and the same inputs. It outputs the cardinality of the union set. One thing to note, with the result of the PSI-CA protocol, one can easily get PSU-CA by the following equation. In this paper, we will focus on the PSI-CA protocol. For these protocols, we have the following privacy requirements. First of all, the server privacy. Client knows no information beyond the cardinality of the set intersection or union, and upper bound on the size of S. For the client privacy, no information is leaked about the client set C, and except an upper bound on its sides. Other related definitions in this presentation, we have two Hashi functions act as random oracles, H1 and H2, and two random data permutations, which will shuffle the item order of the data set. As to the threat model, in this paper, we will focus on the semi-honest model. In the semi-honest secret model, the protocol parties will follow the protocol. However, they are curious and will try to gain extra information out of the protocol. Thereby, for PSI-CA protocol, there are two kinds of adversary. First is the client adversary. It will try to violate the server privacy and try to gain extra private information. For example, the server's private items or intersection items. The second is the server adversary. The server party of the protocol will try to violate the client privacy. It will try to gain extra private information such as client's private items or intersection cardinality or items. The third part of the definitions, we have the following three security assumptions. First of all is the discrete logarithm assumption and the DTH assumptions. In this discrete logarithm assumption, given j and j to the a, it is difficult to solve a. As to the DDH assumption, these two distributions are computationally indistinguishable. These two assumptions are very common if you have ever done some work in information security. You may be familiar with these two assumptions. For example, DH key exchange and the L-gamma encryption are built on these assumptions. The third assumption is a little uncommon. It's called the one more DH assumption. This assumption we give, even if we give the adversary access to a DH oracle and let him recover V pairs of private data in such form, it can't repair another pair in non-negligible probability. The section 2 is the introduction of the original PSI-CA protocol and why it is wrong. In this paper, the authors proposed a protocol to calculate the private city intersection and the union cardinality, aka PSI-CA and the PSU-CA. This paper's security is based on DDH assumption. It achieves linear complexity in communication and computation. So far, it is still one of the most efficient PSI-CA protocols. Also, it is the most popular PSI-CA protocol based on the Google Scholar search result. Here is this picture is the protocol flow. I don't want to bother you with the details of this protocol. It takes time to understand all these equations and the symbols. So I will introduce. I will show you the intuition behind the protocol and why it is wrong. The intuition behind the protocol is the protocol in the end. It makes sure all the private numbers on both sides go through the same computations. If two input numbers are equal, the final output of these computations should also be equal. In this case, the cardinality of the private intersection plus is 1. Also, due to the DL and the DDH assumptions, the client and the server can't recover any private data from the intermediate results. As to why it is wrong, in this protocol, the protocol made some mistakes. For example, it forgets to map these values, these hashes, to the chosen cyclic group. Without mapping these values to the chosen cyclic group, this computation to strip off the exponent R sub C will fail. So as to how to correct these protocols, in our paper, we map these hash values to the chosen cyclic group by the following computations. And this time, this computation will work to strip off the exponent R sub C. As to how to correct the PSU-CA protocol, we change this output to this equation. The corrections of the extended PSI protocol is the same corrections. The only difference is the last two steps. In the last two steps, the client will send the set T, which is the intersection of TS sub 1 to TS sub W and TC1 to TC V. and set T to the server, and the server will recover the intersection item based on T. The fourth section is the security proof. For the security proof, we will divide it into two parts: the client privacy and the server privacy. For the client privacy, according to the threat model, the server adversary will try to recover private data from the client. The private data from the client can be also further divided into two classes: the non-intersection data and the intersection data. For the non-intersection data, because of the hardness of DLP, the server adversary can't recover any private data from A sub I with a non-negligible probability. As to the intersection data, it is further divided into the two classes. The first class is the intersection cardinality when it equals 1. We assume the intersection item is C sub I. Because of the hardness of the DLP, the adversary can't recover HC sub I times R sub C from A sub I. The second case is the intersection cardinality n is greater 1. This case, it is secure under the one more DH assumption. Even if we give the server adversary access to the DH oracle and let it recover n-1 pairs of the private data of the following forms, it can't recover another pair and use it to recover the intersection item. The second part is the server privacy. According to the threat model, the client adversary will try to violate the server privacy by recovering private data from the server. The private data from the server is also divided into two classes. The first one is the non-intersection data. Since H2 is modeled as the random oracle, TS sub 3 is indistinguishable from any random number from Z sub P, so it is secure. For the intersection data, it is divided into two cases. The first case is the intersection cardinality n equals 1. And we also assume the intersection item is C sub I. Because of the hardness of the DLP, the client adversary can't get HC sub I times R sub S. And without the knowledge of R sub S, we also can the adversary also can recover J to HC sub I. For the second case, the intersection cardinality n is greater 1. This is also secure under the one more DH assumption. Assume the intersection item is C sub I1 to C sub IN. Even if we give the server adversary access to the DH oracle and let it recover n-1 pairs of private data of following forms, it can't recover another pair in this form and use it to recover the intersection item. The fifth section of this presentation is the simulation of the protocol and the implementation. The first one is the PSI-CA protocol simulation. We use Python and Linux Red Hat server to do the simulation. This is the parameters of the chosen cyclic group and the two hash functions H1 and H2. Here is the snapshot of the protocol input. We have 1024-bit prime number P and 160-bit prime number Q, and the client's random value R sub C and the server's random value R sub S. This is the private set input of client C, and the server's private input set S. In the protocol output, since we have three intersections of TC sub I and TS sub J, the final output of the PSI-CA protocol is 3. As to the implementation of these protocols, we implement PSI-CA, PSU-CA, and PSI protocols in the popular open source multi-party federated learning framework, aka FATE. In GitHub, it has more than 3,000 stars and 900 forks. We use the same environment and the parameters for the implementation. The test data you can find it on this GitHub repository. And the snapshot is we have the output of the PSI-CA protocol, the output of the PSU-CA protocol, and this snapshot is the output of the PSI protocol. And this is the end of my presentation, and thank you.